Вот включил теперь вроде. Там включил, а тут не включил. Ну ладно, я, наверное, быстренько повторю еще разочек, что я сказал, для тех, кто будет смотреть запись. Okay, so this is the definition of a bounded linear operator that was given at the previous lecture. So I would say that a linear operator between normed spaces is bounded if there is a constant c which satisfies this condition. And we know the set of all bounded linear operators from x to y by b of xy. And if y equals x, then we write just b of x. So what we want to do is to make b of xy into a normed space. And we give the following definition. If t is a bounded linear operator, we define the norm of t to be the infimum of all such non-negative constants c. So first of all, we observe that this infimum is always attained. And the reason is that this set is obviously closed. It's a closed subset of the real line. In other words, the infimum is the minimum. And so this infimum, that is the norm of t, satisfies this inequality for each little x in our space. And we now give some other equivalent definitions of the operator norm. Namely, first of all, we observe that we can consider only non-zero vectors here. And if little x is non-zero, we can just divide this by the norm of x, and we get this. Now, what is this? So by the very definition, this is just the supremum of this set. This is the least upper bound for this set. So in other words, this is the supremum of the norm of tx over the norm of x, where x runs over all non-zero elements. Let's now observe that this number can be written in the following form. And when, as little x runs over all non-zero vectors, this expression in brackets runs over the unit sphere. So this supremum can be also written as follows. This is the supremum of the norm of t of x over the unit sphere. And finally, it's a very simple exercise to show that we can replace here the unit sphere by the unit ball. And the supremum will be the same. This is a simple exercise for you. So we have some other equivalent definitions of the operator norm. By the way, a warning, an important warning. I would like to stress that in general, this supremum is not necessarily attained. The supremum over the unit sphere, is not always attained. And actually, we will have many concrete examples of operators for which this supremum is not attained. This supremum, and this supremum, none of them is attained in general. Of course, there are some operators for which they are attained, but in general, this is not the case. Okay, now let me say a few words about isomorphisms of normed spaces. Actually, we have two types of isomorphisms which preserve either topological properties or metric properties of normed spaces. We will need some notation. If t is a bounded linear operator from x to y, then by the image of t, we always mean its set theoretic image. its theoretic range. It is the image of T. For those of you who are familiar with the language of categories, I'd like to stress that this image is different from the category theoretic image. So the category theoretic image in the category of normal spaces is the closure of the set theoretic range. Well, anyway, for convenience, I'll stick to this notation. So I always, by the image, I always mean the set theoretic image. Let's now give the following definition. So again, we suppose that T is a bounded linear operator from X to Y. And we say that T is topologically injective. Topologically injective, or a topological embedding. If T is a homeomorphism of X onto its image. Of course, this is a pure topological property. It makes sense for any map between topological spaces. This is our first definition. Next, we say that T is a topological isomorphism. A topological isomorphism. If T is topologically injective and surjective. The image of T is Y. So in other words, T is a topological isomorphism if and only if it is a linear homeomorphism of X onto Y. Definition 3, we say that T is an isometry. An isometry if T preserves the norm in the following sense. The norm of T of X equals the norm of X. Equivalently, this means that T preserves the metric. And finally, we say that T is an isometric isomorphism. If T is an isometry and the image of T is Y. If T is a bijective isometry of X onto Y. So we see that we have two kinds of isomorphism, topological isomorphism and an isometric isomorphism. And we see that X and Y are topologically isomorphic if there is a topological isomorphism between them. And similarly, we say that X and Y are isometrically isomorphic if there is an isometric isomorphism between X and Y. By the way, the property of being isometrically isomorphic is much stronger than the property of being topologically isomorphic. For example, we have proved at the previous lecture that any two norms on a finite dimensional vector space are equivalent. And it's a simple exercise to show that this result can be equivalently stated as follows. Any two norms, finite dimensional norm spaces of the same dimension are topologically isomorphic. But if we ask, are they always isometrically isomorphic? The answer is no. For example, if we take even two-dimensional spaces and equip them with two different norms, for example, in the previous lecture we introduced a whole family of norms on a finite dimensional space indexed by real numbers between 1 and infinity, including infinity. So if we consider two-dimensional spaces over the complex numbers, then they are not pairwise isometrically isomorphic. So the property of being isometrically isomorphic is much stronger than the property of being topologically isomorphic. Okay. Topologically injective operators are sometimes called bounded below for the following reason. So we have the following proposition. If T is a bounded linear operator from X to Y, then the following conditions are equivalent. Condition 1, T is topologically injective. And condition 2, there is a constant C, a positive constant C, such that the following inequality holds. So actually we have the opposite, the inequality which is opposite to the inequality which appears in the definition of a bounded operator. To prove this result, we may assume from the very beginning that T is injective. For the simple reason that if T is not injective, then 1 doesn't hold and 2 doesn't hold. So condition 2 obviously implies that T is injective because, well, a linear operator is injective if and only if the kernel is trivial. So, but if X is in the kernel, if this is 0, then this is also 0. So the norm of X is 0, and so X is 0. So condition 2 also implies that T is injective. So if T is not injective, then there is nothing to prove. So we may assume from the very beginning that T is injective. And let's denote by T0 the operator from X onto the image of T, which acts by the same rule as T. Essentially the same operator, but we consider it as an operator from X onto the image of T. So T0 is bijective. T0 is bijective. Now condition 1 means exactly that T0 inverse is continuous. So T0 is a continuous bijection, and it is a homeomorphism if and only if the inverse map is continuous. But T0 inverse is a linear operator, and we know that a linear operator is continuous if and only if it is bounded. And this property is easily seen to be equivalent to condition 2. So if we replace here, say, X by T of Y, so this will be T of Y, this will be Y, and we get by dividing by C, we get precisely the definition of a bounded linear operator applied to the inverse of T0. And this completes the proof. Okay, so let's now come back to the set of all bounded linear operators from X to Y. And as I promised you, let's now prove that it is a normed space. So the following proposition describes the basic properties of the operator norm. Property 1. If S and T are bounded linear operators from X to Y, where X and Y are normed spaces, then S plus T is also bounded. And the norm of S plus T is less than or equal to the norm of S plus the norm of T. So we have a triangle inequality. Property 2, if T is a bounded linear operator from X to Y, and lambda is a number in our base field K, so let's recall that K is our base field, which can be either the field of real numbers or the field of complex numbers. And the product lambda T is also a bounded operator, and the norm of lambda T satisfies the following equality. And finally, property 3, if we have three norm spaces, x, y, and z, and two operators, T acts from x to y, and S acts from y to z, and both of them are bounded, then their composition ST is also bounded. And the norm of ST, the norm of ST is less than or equal to the product of the norm of S and the norm of T. Okay, the proof easily follows from the definition, or more precisely from this equality star here. For example, if we want to prove part 1, we substitute an arbitrary element little x to the operator S plus T. So this is Sx plus Tx. We use the triangle inequality. And then apply the inequality star to each of the summands here. And we get the following estimate. And that's it. So if we look here and we look here, we see exactly that S plus T is bounded, and moreover that the norm of S plus T is less than or equal to this number. Okay, the proof for the second part is almost identical, so I'll leave it as an exercise for you. And actually the proof of 3 is also very easy. Again, if we substitute an arbitrary element little x to the composition ST, then first we apply inequality star to the operator S. So we get the following. And then we apply the same to the operator T. And we get the following. And that's it. So this shows that since this holds for any little x in our space, we look at the definition of a bounded operator and at the definition of the operator norm, and we conclude that indeed the operator ST is bounded and the norm of ST is less than or equal to this constant. Okay, so as a corollary, we see that the space of bounded linear operators from x to y is indeed a normed space. It is a normed space with respect to the operator norm. Okay, let's now look at some examples of bounded linear operators. Ну, ненулевой оператор переводит какой-то вектор в не ноль. Вот, поэтому определение-то. Ну вот, можно сюда посмотреть. Если он не нулевой, то где-то здесь уже не ноль. So if we have a non-zero operator, then its norm is strictly positive because there is a vector x, a non-zero vector x for which this element is non-zero, and so this number is strictly positive, and hence the supremum is also strictly positive. So the norm of a non-zero operator is also strictly positive. Okay, so let's now look at some examples. The first group of examples consists of multiplication operators. We start with the following simple example. Example 1. It is simple but is rather important. This is the so-called diagonal operator. We denote by x any of the sequence spaces that we know. So this can be either the little p space, where p is between 1 and infinity, including infinity, or it may be a little c0. So the little c0 space consists of those sequences which vanish at infinity. So this is the space where our operator acts. And the operator is determined by a bounded sequence alpha. That is an element in the little infinity space. So we define an operator M alpha from x to itself as follows. It takes an arbitrary element that is a sequence in our space to the following one. So it just multiplies x coordinate ways by alpha. So this is a so-called diagonal operator. Why is it diagonal? Well, if we replace here our sequence space by its finite dimensional analog, so we consider only finite and tuples of numbers, then we get an operator in a finite dimensional space, and its matrix will be diagonal. Whence the name diagonal operator. I claim that M alpha is indeed a bounded linear operator on x. And moreover, the norm of this operator equals the L infinity norm of alpha. That is the supremum of the absolute values of alpha n. Let's prove this claim in the case where where x is LP and p is finite. So for the L infinity space or for the C0 space, the proof is more or less the same. So we do the following. First of all, we have to show that M alpha indeed is an operator on x. That is, it takes x to itself. In other words, if little x sits in LP, then this sequence is also in LP. Okay, so we take an arbitrary element, little x in LP, and we write the following sum. So we want to show that this is finite. this will mean precisely that alpha, that this sequence sits in LP. Well, alpha is bounded, so we can replace here, if we replace here each alpha I by the supremum, then we get the following inequality. And this should be multiplied by the sum of xi to the power p. Well, this supremum is finite, and this is precisely the L infinity norm of alpha to the power p. And this is nothing but the LP norm of x to the power p. And this is finite. So this inequality implies that M alpha indeed takes LP to itself. So it is a linear operator from LP to itself. Also, the same inequality shows that this is a bounded operator. M alpha is bounded. And the norm of M alpha is less than or equal to the L infinity norm of alpha. For a simple reason that the left-hand side here is just the norm of M alpha of x to the power p. So when we take the pth root of everything, we see that the norm of M alpha is less than or equal to this constant. So we have this. And to show that these numbers are actually the same, we do the following. For each natural number I, we denote by EI the following sequence in LP. So we have 1 in the ith slot and 0 elsewhere. And we write the following expression. So we, by definition, the norm of F alpha, of M alpha, is the following supremum over the unit sphere. This is one of the equivalent definitions of the operator norm. Now we see that each EI sits on the unit sphere. The norm of this vector is 1. So if we consider only them here, we get the following inequality. Because this is a proper subset of the sphere. But what is M alpha of EI? Clearly, each EI is an eigenvector, and the respective eigenvalue is just alpha I. So we have the following expression. But the norm of EI is 1, so the norm of this is just the absolute value of alpha I. And this is the L infinity norm of alpha. So we have this inequality, and we have the opposite inequality. And they together imply that the norm of M alpha is exactly the norm of alpha. And this completes the proof. Okay, so this is the diagonal operator. Again, I'd like to stress that this is a rather important example. In fact, maybe I'll make a little announcement. One of the central results of our introductory course, which will be proved in the end of the course, is the so-called Hilbert-Schmidt theorem, which tells us that each compact self-adjoint operator on a Hilbert space is unitarily equivalent to a suitable diagonal operator acting on the little L2 space. So this example actually describes a very large and important class of operators. Okay, now example 2, which is in fact even more general than example 1. Suppose now that we have a measure space, omega mu, measure space, to avoid pathologies, let's assume that it is sigma finite, which means that omega can be written as a countable union of sets of finite measure. And suppose that f is an essentially bounded measurable function on omega that is an element of the Beagle infinity space. We take an arbitrary p between 1 and infinity, and we define a linear operator mf on the Beagle p space which acts by the following simple formula. Mf of g is just the pointwise product of f and g. A useful exercise, which is actually already in the exercise sheet 1, is to show that mf is indeed a bounded linear operator on LP, and that the norm of this operator is exactly the L infinity norm of f. That is the essential supremum of the absolute value of f. This norm was defined at the previous lecture, and you can also find the definition in our first exercise sheet. By the way, let's observe that example 1 generalizes example 2 generalizes example 1, because if omega is countable, that is a set of natural numbers, mu is the counting measure, which means that the measure of a set is just the cardinality, then the big LP space becomes a little LP space, f is just a bounded sequence, and this multiplication operator mf is nothing but the diagonal operator from example 1. So example 2 is more general than example 1. And it is also very important. Another classical fact, and this is not precisely an announcement because the respective fact will be proved in the second part of our course, in the operator theory course, which will be given in the spring term. So one of the central results of the classical functional analysis is the so-called spectral theorem, which says, among other things, that if we have an arbitrary bounded self-adjoint operator on the Hilbert space, then it is unitarily equivalent to the multiplication operator on the big L2 space on a suitable measure space omega. So this example is also very important. The next group of examples consists of shift operators. In Russian, operator сдвига. Example 3. So as in example 1, we take either the little p space, where p is any real number between 1 and infinity, including the infinity, or the little c0 space. And we define two operators on x The first one will be denoted by TR from X to itself, and it acts by the following formula. TR of X, well, maybe, let me write this more explicitly. So TR takes each sequence X1, X2, and so on to the following one. So it shifts everything to the right by one position, and it puts 0 in the first position. This is the so-called the right shift operator. The right shift operator. In Russian, оператор правого сдвига. And the second one will be denoted by TL. And it acts by the following formula. It shifts everything to the left, and it eats the first coordinate. This is the left shift operator. So what can we say about these operators? Clearly they are linear. Moreover, TR, the right shift operator, is actually in isometry. TR is an isometry. Clearly the norm of this sequence equals the norm of this one. By the way, this is a classical example of an isometry which is not surjective. TR is an isometry, so the norm of TR is 1. Clearly the norm of any isometry is 1. TL is not an isometry. In the general case, the norm of this one is less than or equal to the norm of this sequence, because we have no x1 here. But on the other hand, it's obvious that the norm of TL is also 1. Because we can easily find an example of a sequence for which these norms are the same. We can take any sequence for which the first coordinate is 0, and TL preserves the norm of each sequence of this form. So its norm is exactly 1. By the way, TL is a classical example of what we will later call a coisometry. This is a class of operators which is in some sense dual to the class of all isometries. Okay. One more example, example 4. Example 4. Now let x be either the literal p over the integers, Lp of z, or we can also take C0 of z. I didn't define these spaces formally, but the definition should be clear from the notation. So we just take the definition of the literal p space and replace the natural numbers by the integers. So the space consists of those sequences which are indexed by integers, so they are infinite in both directions, and such that the sum of the p powers of the absolute values is finite. And similarly, C0 of z is the set of all two-sided sequences which vanish at infinity. We define an operator T B on X by the following formula. The ith coordinate of TB of X equals the to xi minus 1 for all I in Z. And this operator is the so-called bilateral shift. In Russian, двусторонний сдвиг. The title, the name of this operator is a little bit misleading because actually, if you look at the formula, you'll easily see that this is actually the right shift. It moves everything to the right by one position. And is the only reason why it is called the bilateral shift is that the sequences here are two-sided sequences. But anyway, maybe the name is not very good, but it is a standard one. So usually this operator is called the bilateral shift. So what can I say about this operator? Clearly, this operator is a bijective isometry. Or equivalently, an isometric isomorphism of X onto itself. So it moves everything to the right, but since the sequences are two-sided, obviously it is bijective. The inverse map is the left shift. So we just replace I minus 1 by I plus 1, and this will be the inverse map. And clearly it preserves the norm. So it is a bijective isometry of X onto itself. In fact, this example is a special case of a huge variety of examples of shift operators which act on function spaces on locally compact topological groups. Here's another example of the same kind. Example 5. Let's now denote by X the space, the big LP space over the real line. So by default, the real line is equipped with the Lebesgue measure, usual Lebesgue measure. Or we can also take the space of continuous bounded functions, CB of I. We now take a real number little a, and we define the operator TA on X by the following formula. Well, since the Lebesgue measure is translation invariant, it's easily seen that the norm of this function is equal to the norm of f. So TA is an isometry, and is obviously bijective because the inverse map takes f to f of t plus a. So TA is a bijective isometry. And one more example of the same kind, example 6, is the shift operator on the circle. So let's denote by bold T the unit circle on the complex plane centered at 0. Basically, this is a circle. So topologists denote the circle by S1, but the difference is that I want to stress that it's not just a topological circle. Here we consider the circle as a topological group, and this leads to the difference in notation. So bold T is the circle considered as a topological group. We will equip it with a standard measure. Informally, this is the usual length measure on the circle divided by 2 pi. This is the so-called normalized length measure. We normalize the usual length measure in such a way that the measure of the whole circle is 1. And we denote by X the big LP space over the circle with respect to this normalized length measure. Or we can take the space of continuous functions on the circle. And we fix an arbitrary number zeta on the circle. And we define an operator T zeta from X to itself by the following formula. So in some sense, this is just a change of variable. We just rotate a circle and substitute f to f, substitute to f to the result of this rotation. And since the length measure on the circle is well known to be rotation invariant, we see that the norm, the LP norm of this function, is equal to the LP norm of f. So T zeta is a bijective isometry. Again, the inverse map is given by the same formula. We simply replace zeta by zeta inverse. Okay, and another important class of examples consists of the so-called integral operators. Historically, this is perhaps one of the first classes of operators which was studied systematically. And such operators have many applications to integral equations and to differential equations. And this is one of the reasons why they were studied already at the beginning of the 20th century. Okay, so suppose we have a measure space, omega mu, measure space, and suppose that X is some vector space whose elements are measurable functions, or to be more precise, equivalence classes of measurable functions on omega. So there are many vector spaces, many normed spaces with this property. For example, we can take the big LP space over omega, where P is between 1 and infinity. If omega is, for example, a subset, an interval on the real line, we can take the space of bounded continuous functions, and if this is a closed bounded interval, we can take the space of all continuous functions on omega. So there are many possibilities for such a space X. Suppose now that suppose now that T is a linear operator on X. By definition, we say that a linear operator T from X to itself is an integral operator if there exists a measurable function K defined on the product omega cross omega. So this is a function of two variables to our base field K, such that the operator T acts by the following formula. T f of x is the integral over omega K of xy f of y with respect to the measure mu. So here f is an element of our space, and little x is a point in omega. So if such a function k exists, then we say that T is an integral operator. And the function k is called the kernel. It's the kernel of T. Of course, this shouldn't be confused with the preimage of 0, which is also called the kernel. So this is just a simple coincidence. The name kernel is used for two absolutely different objects. Another closely related class of operators consists of so-called Voltaire operators. So from now on, let's assume that omega is, we call the interval AB of the real line, and mu is the usual Lebesgue measure. And suppose that we have a linear operator, as denoted by V, from X to itself. We say that V is a Voltaire operator. If there exists a measurable function K on the square such that V acts as follows. Vf of x is the integral from a to x, k of xy, f of y, dy. As usual, since we integrate over the Lebesgue measure, we suppress the explicit notation for mu. So we see that the formula is somewhat similar to this one, but the difference is that here we integrate over all of omega. And here we integrate not over the interval from a to b, but we integrate only from a to x. That's the difference. By the way, let's also introduce following notation. So if T is the integral operator determined by K, then they write it denoted by TK. And similarly, if V is the Voltaire operator determined by K, we denote it by VK. So in fact, it's easily seen that the Voltaire operator is a special case of an integral operator. Let's observe that the Voltaire operator, Vk, is the integral operator whose kernel, let's denote this respective kernel by k tilde, is defined as follows. K tilde of xy equals k of xy if y is less than or equal to x and 0 elsewhere. So here's the picture. So this is our square from a to b. So k tilde equals k here and 0 here. It's easy to see that if we integrate k tilde from a to b, and this is the same as if we integrate k from a to x. So the Voltaire operator becomes a special case of the integral operator. Well, of course, these two definitions just describe some classes of operators axiomatically. They describe some properties of the operators. And of course, I don't claim that this formula makes sense for any measurable function, k, and for any vector space X of measurable functions. Of course, this is not the case. In order for these operators to exist, we must impose some conditions on K and on our space. And here are some examples of such conditions. Example 7. This is a concrete example of a situation in which both the Voltaire operator and the integral operator exist. So let's denote by I the closed interval from A to B on the real line. Let X be the space of continuous functions on this interval equipped with the supremum norm. And suppose that K is also continuous. K is also continuous. It's a simple exercise, and this is an example and exercise at the same time. So the exercise is to show that both Tk and Vk are bounded linear operators on X. I'll try to estimate the norm. Actually, when you prove that the operator is bounded, you automatically estimate the norm. If you show the norm is finite, you get an upper estimate for the norm. So this is a special case in which our operators exist. And another special case, which is maybe even more important, is the case where the space consists of square integrable functions, and the function K, the kernel K, is also square integrable. This is a so-called Hilbert-Schmidt integral operator. This is example 8. The Hilbert-Schmidt. Integral operator. Again, this is an example and an exercise at the same time. It will be included in the next exercise sheet. So suppose that omega is an arbitrary, well, for simplicity, sigma finite measure space. A sigma finite measure space, and K is a square integral function on omega cross omega. And X is the space of square integrable functions on omega. Well, for references, as you know, this integral by 1. So I suggest you to prove the following. First of all, for each f in L2, this integral exists for almost all x in omega. For almost all x in omega. So this function is well defined almost everywhere. And we can easily extend it somehow to the whole space, just, for example, by letting it 0 in the space, in the points where it is not defined. So this function is defined almost everywhere, and actually this function is square integrable. So T becomes a linear operator from L2 to itself. And part 3, try to show that T is bounded is a bounded linear operator from L2 to itself, and that the norm of T is less than or equal to the L2 norm of K. Well, yeah. This is true for any sigma finite measure space. Okay, let it be sigma finite. I just had an idea to remove the condition of sigma finiteness, but the proof involves the Wvедение theorem, and Wvедение theorem is usually proved for sigma finite measure spaces. Okay, so this is an exercise. Okay, we still have 10 minutes left, so let's now begin to discuss a very important special class of normal spaces. Namely, let's discuss Banach spaces. So the definition is as follows. A Banach space is a complete normed space. Complete, I mean complete in the metric sense. That completeness means that each Cauchy sequence converges. Banach spaces are named after the great Polish mathematician Stefan Banach, who was one of the founding fathers of modern functional analysis. And it turns out that Banach spaces are even much more important than arbitrary norm spaces. And the reason is that there are many beautiful and deep results on Banach spaces which don't hold for incomplete norm spaces. Well, let's look at some examples of Banach spaces. Of course, the first obvious example is our base field of real or complex numbers. So of course, you know from your standard calculus course that this space is complete. So each Cauchy sequence of real or complex numbers has a limit. Example 2, which is also probably familiar to you, we can take Kn with a standard Euclidean norm, and this space is also complete. So it's a Banach space. Now, the natural question is, what happens if we replace here the Euclidean norm by some other norm on Kn? And the answer easily follows from the following proposition. Suppose that x and y are normed spaces, then part 1, if T is a bounded linear operator from x to y, then it takes Cauchy sequences, two Cauchy sequences. If xn is a Cauchy sequence in x, then its image Txn is Cauchy sequence in y. And part 2, if x and y are topologically isomorphic. Topologically isomorphic. And one of them is a Banach space. Say X is a Banach space. Then so is Y. Y is a Banach space. So the completeness of a normed space is a linear topological invariant. By the way, you probably remember that the completeness is not a topological invariant. It's not preserved under arbitrary homeomorphisms. But it is preserved under topological isomorphisms of normed spaces. And it is preserved under linear topological isomorphisms. The proof is very easy. The first part is immediate from the following inequality. So by the definition of the operator norm, we have this inequality. So if xn is a Cauchy sequence, then this distance is as small as we want if n and m are big enough. So we just multiply this by a constant, and this readily implies that this is also a Cauchy sequence. And part 2 easily follows from part 1. If we want to show that y is complete, we take a Cauchy sequence in y, apply, so we take a topological isomorphism between x and y, and we apply the inverse operator, T inverse. So T inverse by part 1, T inverse of ym is a Cauchy sequence in x. But x is assumed to be complete, so this sequence converges to some element little x. And then we just apply the operator T, which is continuous because it is bounded. And we see that yn converges to T of x. And this shows that y is complete. So the completeness is a linear topological invariant. And here's a useful corollary. Corollary 1. If x is a vector space, and if we have two equivalent norms on x, two equivalent norms, then if x is complete under the first one, this is a Banach space, then we can replace this norm by the second one, and we still have a Banach space. This is immediate from the previous proposition because since the norms are equivalent, the identity map from here to here is a topological isomorphism. And so the completeness is preserved. Now corollary 2, which follows from corollary 1, a finite dimensional normed space is always a Banach space. A finite dimensional normed space is a Banach space. Well, indeed, we already know that all norms on a finite dimensional vector space are equivalent. So since our space is finite dimensional, we can assume that it is just Kn for some n. But we already know that there is a norm on Kn such that Kn is a Banach space, namely the Euclidean norm. And now corollary 1 implies the result. So a finite dimensional norm space is a Banach space. And in conclusion, let's recall another important example of a Banach space, which you also know either from your calculus course or from your topology course. This is example 3. If X is any set, then the space little than infinity of bounded functions on X equipped with the supremum norm is a Banach space. This is a standard result, and I'm assuming you know this fact. And the very last example, example 4, which is also known to you, if X is any topological space, then the space of continuous bounded functions on X, CB of X, is closed in infinity of X. In classical terms, this means that the uniform limit of a sequence of continuous functions is continuous. But a closed subset of a complete metric space is also complete. So since this is a Banach space, we conclude that CB of X is also a Banach space. Okay, so that's all for today. The next lecture, we give some more examples of Banach spaces. And we discuss some nice properties of Banach spaces, which generally don't hold for arbitrary norm spaces. Thank you.